Okay, going to have a look at some nucleophilic additions to carbonyls. So the first thing I'll have a look at is reduction, and the second thing we'll have a look at is the reaction with hydrogen cyanide. So if we start with nucleophilic addition and reduction, we can use sodium tetrahydroborate 3 to provide a hydride ion to reduce aldehydes and ketones to their corresponding alcohols. So if you've got an aldehyde and you reduce it, you're going to get a primary alcohol, and if you've got a ketone and reduce it, you get a secondary alcohol. The type of reaction then is called reduction, and the mechanism is a nucleophilic addition. So if we're looking at reducing the carbonyl, just to remind you, the carbonyl group is trigonal planar, opportunity for the nucleophile to attack above and below the plane of the carbon. So the nucleophile can attack from both above or below the carbonyl group, and the attack is on the electron deficient carbon. So if we have a look at ethanal, we know that oxygen is more electronegative than carbon, so that's a polar carbonyl group. So it's delta plus on the carbon and delta minus on the oxygen. So the carbon is electron deficient and therefore is attacked by our nucleophile. So if we're having a look at reduction, we don't write anything with sodium tetrahydroborate, we just write the hydride ion. So I've shown the hydride ion there as the nucleophile is the H- ion. So initial attack is for a lone pair of electrons from the hydride ion attacking the electron deficient carbon with the movement of the pi electrons in the carbonyl onto the oxygen. So the intermediate has a negative charge on the oxygen, and you can see the lone pair there. What will happen next is you form a hydroxy group by reaction with hydrogen ions which are formed in the solvent. So the second hydrogen there in the reaction is the hydrogen ion. When you're writing equations for this, you're not expected to write them with sodium tetrahydroborate. You can just use hydrogen atoms in square brackets, so you would use an H in a square bracket, but make sure that you add appropriate number so your equation balances. So in this case, if I started with ethanal and I'm making ethanol, I'd have to write 2H plus H in a bracket, In the same way, we can reduce ketone to a secondary alcohol. So we start with propanone. We've got the initial nucleophilic attack from the hydride ion made from sodium tetrahydroborate onto the carbon, and then the respective move of the pi electrons onto the oxygen. So exactly the same mechanism where the O- is then and the pair of electrons attack the hydrogen ion from the solvent, and we'll get a secondary alcohol. Second type of reaction, which is nucleophilic addition, are reactions of aldehydes and ketones with hydrogen cyanide. In this case, the hydrogen cyanide produces a Cn- ion, which is the nucleophile. So you notice on the Cn- ion that you put the lone pair on the carbon and the negative charge on the carbon. So the mechanism is exactly the same again, with the initial attack of the nucleophile on the electron deficient carbon, forming the intermediate, which then gets protonated by the solvent. The type of product you get in these reactions are called hydroxynitriles, and you'll notice also that you increase the chain length. So if you're starting with ethanal, you end up with a 3-carbon hydroxynitrile. So if I'm naming this hydroxynitrile, it'll be 2-hydroxypropan-E-nitrile. This nucleophilic addition and will add a carbon to the chain, so ethanal becomes 2-hydroxypropanitrile. If you have an asymmetric ketone, you can produce 2 enantiomers. These are optical isomers and are non-superimposable structures. These form as there is a 50-50 chance of the nucleophile Cn- attacking above or below the planar carbonyl to give a tetrahedral carbon with 4 different functional groups. So we often show this with like A, B, C, D. It doesn't matter which group you put where, as long as you've got your mirror image, so you end up with the 2 enantiomers, which are non-superimposable mirror images. The carbon is called an asymmetric or chiral carbon, as often shown with the asterisks on the carbon. If we have a look at an example of this, we would have butanone there with the attack from a Cn- ion. It can attack 50% chance from above or 50% chance from below, so we end up with the same nucleophilic addition reaction, but it'll actually form the asymmetric carbon. So I've shown that as carbon 2 there. So we're making 2-hydroxy 2-methyl butanitrile which is going to form two optical isomers. So I've shown the 4 different functional groups. We've got the hydroxy group, we've got a CN group, we've got a CH3 group and a CH2CH3 group. So it doesn't matter where you put them as long as you end up with the mirror image. So in actual fact we get optical isomers as a product here. Quite often the CN group there, the nitrile group, is hydrolyzed further to form a carboxylic acid. So you could use phosphoric acid there to increase that to a carboxylic acid in one of the synthetic routes. So if you have a look at the toolkit, you'll notice that you would get chain elongation, often through a nitrile towards a carboxylic acid.